So that's why I put them together. For different layers, we give a different name here. And also we describe the action when you look into the name, what they are really doing, okay, and what's the effect. And also, they have some, if you draw layout, later on they will be sent out for mass fabrication. So as we mentioned, there are two types of files accepted for mass fabrication. One is a zip file. The other one is a GDS2 file. On the zip file and GDS2 file, each layer, each different structure layer, they have a different name, okay? And the GDS2 file given numbers, okay, for different layers. Just give you some idea. And they also show showing on your edit layout software with different colors. Okay, so on the left column, I give you the colors of each layer. Okay, now we go back to the name. Okay, so we put them into the list, just following the fabrication process from the beginning to the end. Okay, so the first action, remember, we have done is by define the active region, right? When we define the active region will be deposited by silicon nitride for protection. But the rest of the area will have the field oxide growth. So when we talk about active, that means on the active region, you have silicon nitride deposition. And then no field oxide grow on top. Okay, these two meaning together. Okay, means active. So after that one, we have N-well. N-well means that region we will dope it with N-type material, for example, like phosphorus or arsenate. And then N-select and P-select. That means we want to dope this region as either NMOS or PMOS device. N-select means we'll select the region to deposit N+. P-select means we select the region to deposit P+. So unselect P-select means we do doping. We do doping process. Okay? Then we have a very thin gate oxide grow on the top. Okay? Then we have a polysilicon deposition and definition. So poly means polysilicon deposition. On the polysilicon, we have polyoxide and have a poly 2 and oxide 1. So polyoxide and the poly 2, sometimes you don't need to consider them because in CMOS process, if you need only one polysilicon, you can neglect these two layers. But in MEMS process, sometimes we may consider use them because you want to have a thicker polysilicon. Maybe you can consider to connect them to each other. Okay? But remember, there's always a polyoxide between these two polysilicon. There is no way to remove this polyoxide, no mask between them. Okay, no masking possible between them. So you have these two deposit together. They will not be connected to each other actually. Now, after the polysilicon deposition, we deposit the first oxide layer for protection to separate the polysilicon to the later on metal material. Okay, so the oxide 1, after deposit oxide 1, actually we need to, in order to connect the rest of the material into the bottom substrate. So there are several special things. We call the poly contact, poly 2 contact, active contact. So those actions are punch holes on the top of oxide 1 layer. So these three processes are actually etching process. And oxide 1 process means it's a deposition process. Poly is a deposition process, gate oxide deposition process, N-select, P-select, those are doping process. But the poly contact, when you see the contact, that means a punch hole, okay? To leave the hole, okay, on oxide 1. Poly contact means you do the etching, okay? So the action is for metal to connect to poly polysilicon, the first polysilicon. We call it poly contact. So these three contacts have different depth. The depth is different. For poly contact, he do the dry etching only down to the polysilicon. So we will punch. So the poly contact will punch through oxide 1, poly 2, and the poly oxide, stop on the top of the poly. So poly contact means if you execute this action, actually you will allow the metal one to directly contact with the polysilicon. So the same can be applied to poly 2 contact. If you execute the poly 2 contact action, you will punch through oxide 1 and directly, that's it, directly expose the poly 2. So the metal 1 can be connected to poly 2 directly. So the poly 2 contact, the depth is thinner, okay? It punches through only oxide 1 layer. But for poly contact, it's thicker. It punches through 3 layers, including oxide 1, poly 2, and the poly oxide, these 3 layers. And then for the active contact, it's much thicker. Not only the previous 3 layers, it also needs to punch through the polysilicon until the metal one can contact to the active region directly. So you need to cut through all the rest of the area from oxide 1, poly 2, poly oxide, polysilicon, and even gate oxide until the metal contacted with a a P select or unselect or P select, the active region. So active contact is the thickest one. It will punch through 4 or 5 layers. Poly 2 punch through only 1 layer, and the poly contact punch through 3 layers. Okay? So these 3 contacts in your figure is showing similar. They are black field. So you cannot tell the difference from your mask. That's very dangerous because you don't know which is which from your layout. But when you do the mask separation, they can separate into 3 different masks automatically because they are defined in different numbers here. But on the figure, they look the same. So remember, it's important to make sure what kind of contact you are drawing. Otherwise, you will contact to different layers easily. Okay? So their number are different, their name are different, but their looking are the same. Okay? They are black. Okay? So after that, we have a metal one deposit on the whole surface. Because we have defined several areas with poly 2 or active contact. So when the metal deposit onto the whole surface, those whole area can also accommodate the metal inside the hole for connection. Okay? So the metal one is a blue field, is blue. The color is blue, is easy to recognize. After metal one, you deposit metal oxide 2 for the protection of the metal one and the rest of the area. And also, you want to connect the metal 2 to metal 1, you also need to punch the hole. The hole is easier because we need to punch through only 1 layer, oxide 2 layer. So there's only one kind of a contact we call a vial. Okay, we call it a vial. The vial means the contact between the metal 2 to metal 1. But remember, don't connect your metal 2 directly onto the bottom because that will cause an over-etching problem. So always connect metal 2 to metal 1 and using metal 1 to approach other different layers. Because we are using a lot of dry etching process. The dry etching process are easy to damage the bottom material. In the next homework, you will do some practicing. When we have some over etching, what will happen? You will see that there are much difference. Because if you don't consider the over etching, you never find out that the final real result will the same as your design. Will be very, very different. Okay, so by doing that homework, you will understand how serious it is. Yeah, the probably need to work close. So for metal 1 connect to metal 2 to metal 1, you need to punch through oxide 2 layer. So we're using VIO, okay? The VIO is white field, so it's much better because in the previous one, all three are in black. So this is in white, so you can differentiate the difference between this one and the previous 3 contact, okay? It's in white, okay? The metal 2, the metal is gray, okay? Then the pad, okay? Pad means when you have a device fabricated inside the local region, actually when you want to input a signal, you need to draw the line. The line is pretty thin and pretty small. So you need to open up a large area for your outside wire to contact with that region, and the signal can be introduced into your device. So those regions we call the pad. So the pad size is larger than your device. Sometimes your device is only like tens of micron overall in size. But tens of micron, you connect the wire is only like several micron, like 2 micron, even 10 micron maximum. However, you want to connect the outside large wire into a 10 micron wire, it's not possible. So you need to extend the very narrow wire into outside to the boundary of the chip and open up a large area for the connect of your real wire into the device. So those regions we call the pad, bonding pad, for wire bonding. The wire is usually around like 25 micron in thickness. So the bonding pad usually is larger than 100 micron. But even 100 micron, you can imagine, is still quite small compared to your hair. It's only half of your hair diameter. It's quite small. So you can see that only under the microscope and do the wire bonding, okay, process. So the wire bond area usually is on the border, on the outside of the chip. So you need to connect the device using the wire to the outside and do the wire connection. Do you understand? To fan out. Okay, so those are pad, okay? So you need to define the pad area. For the pad area, actually, and also the overglass. So the overglass, okay, you want to connect the outside wire into the metal tube. You need to cut through the overglass. Overglass means you already deposit a final glass, silicon dioxide on the whole overall surface. So using this command, okay, to open up the area for your wire to connect to the pad region. So the overglass, the meaning is similar to your VIO, to puncture hole. So overglass means a puncture hole on the outside overglass. But the hole is usually large, okay, because you need to connect the outside wire into the region. So the overglass is also thick and the region is large. So you can draw overglass on that region to open up for outside connection. Do you understand? It's okay? Maybe. Okay. Okay, so they have different color. So in a specific homework, you need to go through this process maybe more than 100 times in your head, in your mind, in order to finish the homework. Because they will tell you some kind of different, overarching rule, and also have different kind of conditions of a different material on top of the other material. So when you want to consider the final results, you need to go through each step by step, and consider the etching process, what will be going on over there, what kind of a thickness that will remain on the surface. So you need to go over the whole steps more than 100 times. So they will give you a chance to practice a lot, actually, before you do the real design. Without this ability, I think it's very difficult for you to do the real design. If you're not familiar with the detail of this process, it's important. Yeah. So it's a painful process. I have been through that process before. I understand how painful it is, but it's important. Yeah. So if once you get through this process, you will have ability. You don't need to go back to the figure to visualize them one by one. all the figures will be deep in your mind. So you can pop up the idea very quickly. Afterward, you can do the design by your intuition directly. It becomes part of your intuition later on, okay? But not now, okay? So you need to do some practice. Okay, some useful things I need to mention here is the first one, in IC processor, that's it, okay? Nothing more. But in MEMS process, sometimes we need to open up some area for bulk machine etching, right? To leave the silicon outside. Because currently we have 4 layers of oxide on the surface to protect the surface. So if you don't punch the holes on that area, you really cannot expose the silicon area for later on bulk machine etching. So the way to open up to expose the silicon surface is by, we call the pit action. The pit action actually is a 4 action work together to form the process. The first one, we define that area as active area. That's the first step. That means in that active area, we won't have any field oxide growth. Remember, we have 4 oxide layers over there on your surface for protection, right? You have field oxide, oxide 1, oxide 2, and over glass, 4 oxide layers. So now you want to expose the silicon, you need to open up these 4 layers. Okay? So that means first you need to define the area as an active area. So there will be no field oxide growth. The second one, you need to punch a hole on oxide 1. So we call the CCA. CCA, the name is a SIF name. We look at CCA, that means the active contact. CCA is here. Yeah, active contact. The first C means a SIF. CA means a contact to active area. This is a kind of abbreviation for the name. Okay, so you can look into the name to try to guess what has the meaning. For example, like CCP. CP means a contact to polysilicon. CE means a polysilicon 2. Okay, CVA, VA means VO. Okay, so from the SIF abbreviation name, you roughly can guess what is that. CMF, that means first metal. MS means the second metal. So it's quite clear. This means pad. And also like the N will N, the N select, P select. It's quite straightforward actually. Yeah, it's easier to talk about the abbreviation rather than the long name individually. Okay. So now the pit means we will open up the area to expose the silicon. So we will do 4 action. The first one defined as an active region. Then take out the first oxide. Take out second oxide. VO is the second oxide layer. And take out the overgas. We call it COG. OG means overgas. VA means VO. CA means the contact to active region. So we perform these 4 together on the same area. That means that area, you won't see any other material. You see only silicon over there. Okay? So later on, when you expose this area into the KOH or EDP, the KOH can cut through the material itself directly. And if you have like a cantilever beam structure, you can release the cantilever beam after the bulk machining process. Okay, so that's the first thing you need to understand. There's a difference from the IC process. Okay, another thing you need to notice is usually in the fabrication process, there's always a consideration of 20% over etching. The over etching means when you do like 1 micron etching on your polysilicon, 0.5 micron etching on polysilicon, because the opening area is different from one to the other. So in order to make all the area can be clear up at the same time, so we will over etching a little bit to allow some slower region can be the etching can be finished at the end of the process. But for the fast etching area, the 20% over etching can give you some damage to the bottom material. That's a problem. But that really depends on what kind of bottom material you have. For example, for polysilicon etching, if your bottom material is a silicon oxide, the silicon oxide can be damaged as well because dry etching does not pick up what kind of material they are. They usually can be stopped only by metal, but not by dielectric material. So you have a polysilicon material, underneath you have a silicon dioxide material. So when you etch in the polysilicon material 0.5 micron, you also take down like a 0.1 micron on the bottom silicon oxide material. But the bottom silicon oxide material sometimes is very thick, it's 0.85. So you take out 0.1 is okay, 0.1 is okay. But sometimes it's very thin, like a gate oxide only 10 nanometer. It's not allowable to take only 0.1, nothing left. So that's a problem you need to consider, okay? But if under the polysilicon there are metal structure, there won't be problem because metal can stop the dry etching. But in the CMOS process, there's no metal under the polysilicon, as you can see. So all the process under the polysilicon, the material can be easily etched by the polysilicon etching process, the dry etching process. So consider the 20% over etching sometimes is harmful, can damage a lot of material underneath, okay? And that will cause the outcome will be very, very different from your original design, okay? So there was, this point will show up in your homework, the very difficult homework, very painful homework. The homework you need to go through 100 times of preparation process. Yeah, it's caused by the over etching, the issue of over etching, okay? So you will practice this. Also, I will show you some design rules, simple design rules for the MOSFET scan 2.0. The line size you cannot design smaller than 2 micron, okay? And the space is 2 micron for polysilicon. The metal one need to be larger and also wider, 3 micron. And the metal two, the space even need to be a little bit larger, okay? 3 micron, 4 micron. For the active region, smallest one is 3 micron, space 3 micron. And the P-select, N-select to well, 5 micron. So the select area or the piece, the well area need to be larger than your active region, as you know, because when you do the alignment, there's always some misalignment. So you need to have some tolerance to the misalignment, okay? And the pad usually is 100 micron, okay? The smallest distance between the pad will be 50 micron, cannot be too close to each other. And the pad to metal, like 10 micron, and the pit, 20 micron, okay? The size of pit. Usually, sometimes we can design the pit larger than this one, so don't consider this as a very strict rule, only for your reference, okay? So the pit can be larger, no problem, actually. But for the rest of the one, they are very strict. When you design these kind of things smaller than the gap or the distance or line width, as they mentioned here, when you do the design rule checking, they'll give out an arrow over there. So if you don't change the distance, don't change the line width, the arrow will always over there. So when you send out for the method fabrication, they won't allow you to do the fabrication. So you need to fix all the arrow before you send out the fabrication. But the arrow will happen on those polymetal and active region. But I think it's okay for pit. The pit is a special design for only for mass. If you have some arrow on the pit, it's okay. But it's not okay on other different material and layers. Is it clear? Okay. So this is a very simple one. For the more detailed one, you need to check their books. Actually, design rules can give you books that thick, yeah, including TSMC. Usually come out with a book, including the 100 pages for very, very detailed design rules. So for simple men like me, I cannot remember all those kinds of things, okay? So I usually just follow the easy design rule. And I'm using the design rule checker to give me the information about which part is not correct. And I do the correction until there's no error showing. That's the way I am doing design. Otherwise, I think there's no people otherwise can remember so many design rules in that much detail. Okay, just remember the simple one. That's okay. Okay, so now we after the fabrication of the CMOS chip, you got a device back. So the IC part is workable, no problem for you. However, the MEMS part before the releasing is still fixed on the surface. It's not movable, so it's not working. So it's important after the fabrication of the MEMS CMOS chip, you need to do releasing process. So the method for bulk machining to release a structure, we can by using EDP or TMA, but not a KOH, because KOH is very corrosive to your silicon dioxide and also the metal films. So don't use KOH, okay? So only allowable is EDP or TMAH. TMAH, the property is similar to KOH, but it's mild. It's more mild. And then also you can use EDP, but EDP currently, as I mentioned, is a cancer-caused material, so we don't use that anymore. So the only thing you can consider now is the TMA. Okay, don't use EDP. And another one, those are by using the wet chemical etching. You can also consider by using gas type etching, by using xenon difluoride. But for EDP TMA, they can give you a bulk machining, give it a structure according to the crystal orientation of a single silicon crystal structure. However, for xenon difluoride, it's like an isentropic etching. So there's no direction. So it doesn't matter what kind of crystal orientation you have. So you always punch a hole under your opening, okay? Isentropic etching. So for xenon difluoride, you can open up a large area or take out the material under the cantilever, but you cannot define the boundary clearly because of isentropic etching. So you want to define the cantilever or your structure accurately, you definitely consider by using TMA or EDP, by using bulk machining. There's the differences. But if you want to open a hole, doesn't matter the size, you can use xenon difluoride. It's a gas type etchant, okay? Another thing you can consider by using deep silicon RE. By using silicon RE, can leave a very thick bulk material under your cantilever, for example. For bulk machine, usually you will take out all the silicon under your thin film, the thin cantilever beam. However, you want to leave a thick material underneath. Okay, so you can consider using deep silicon RE to do the etching first, then cut the bottom later. So you got a very thick structure under your cantilever beam. So this can be done by using the deep silicon RE process. And the deep RE and also the side etching process we call the screen process is a very special process. It combines two processes. One is vertical etching, the other one is side lateral etching. These two processes together, and to form this kind of a very high spatial structure inside silicon. Okay. So these three methods are the useful method for you to consider to release the structure with a thin film, either thin film or thick structure. And the other methods you may consider to add material onto the substrate, but not. I don't think that's a good actually process. Not easy to handle. If you don't try to design your structure, not to use this kind of AD material process. Otherwise, give you a lot of trouble. But if you really want to do that, you can consider by using low temperature process. For example, like a metal deposition, photoresist, or some kind of low temperature material, low temperature oxide. So the temperature cannot be more than 250 degrees Celsius. Okay. And also you can consider electroplating. So electroplating, just 电柱, usually is at atmosphere and also the room temperature. You can operate the electroplating easily. So those kind of things can give you a more compatible process to the IC. Okay, so they are examples are the most inverter and the microfan. So for this one, this will be in your homework. So let me show you a little bit about the homework, because this homework is quite difficult if you are the first time to meet with them. You will have no idea how to do that. But actually, the instruction is very clear inside the question. So hopefully you can follow the question. Let's see the last year's homework 4, homework 3. Here, this one. Okay. Okay, so this is a design. The design of the whole system. The system consists of 2 sensors, one sensor here. Sensors here. This is a reference, and the two MOSFET. So this MOSFET, we put the 2 PMOS together and connect the gate to each other. Because we call this kind of infrastructure as we call the current mirror. Current mirror means what kind of current you go through here, then we have a similar current going through the other sides. The 2 sides have parallel current going through, so they are similar to each other. So when you apply high voltage here, and when you lower down the sensor, the gate voltage. Okay, the gate voltage, the V bias, when the V bias smaller, lower than the VDD, okay, the PMOS can be opened up. So when you fix the V bias, you also fix the gate voltage to both of the PMOS. So when you fix the V bias here, and the VDD minus the button voltage here, V sensor here, will also be fixed. So the current going through these 2 regions are fixed. So that's why we call this device, we call the current mirror. So the current mirror will go through 2 resistors here. One resistor we call the reference resistor. The other one is a sensor. So this sensor is actually on the left-hand side, is a MEMS device. Okay, it's not only a resistor. It's a resistor on the top of a cantilever beam. That means that the resistor here is isolated from the bottom substrate. That means the heat transfer for this one is not as good of the other one. The other one is sitting on the top of silicon substrate. Remember, silicon substrate is a very good thermal conductor. Okay? So when you have current going through these two resistors, even though they are the same originally, with the same the resistance, for example, 100, for example, like 1 kilo ohms for each other. However, after you put into the current into these 2 devices, this one will be cooled down by the substrate. So the resistance won't change much if the current going through. However, the other one, you have current going through this device, but this device will be heated up because it's isolated from the substrate. Okay? So this will cause the resistance change. So resistance here now will be higher than the other side when you increase the temperature, or lower, depends on what kind of material. If you're using metal fin, you increase the temperature, will increase the resistance. If you're using silicon, it's semiconductor, you increase the temperature, you will lower down the resistance. It's inverse. Okay. No matter what kind of things are here, maybe currently with polysilicon. So when you heat up the resistance, you have a different. Originally they have a different resistance. So you have originally they have a same resistance before the heating. So the V sensor will be the same as a V reference. These 2 voltage will be the same. However, when you give the current into these 2 devices, these 2 voltage will become different. Okay? will become different. So that's why we want to define some kind of operation voltage for the V sensor equal to the V reference. We need to design originally this resistance a little bit higher than the other one. Originally, a little bit larger than the other one. So when we heat up this one at the normal condition, the resistance will be dropped into the same resistance as this one at the operation point. Okay, so that's only for the preparation. So during the operation, because this is a flow sensor, during the operation, the flow will going through this region. So when the flow going through this region, the temperature of these resistors will be cooled down. Okay. When the temperature cool down, so the resistance will change. Okay. So resistance change will cause the difference of these two voltage. So now you do the measurement on these two voltage difference, you can understand the flow speed, how much flow going through this region. You have a high flow rate, you have a large difference here. You have a small flow rate, there's a low voltage difference here. If you don't have any flow rate, there's no voltage difference here. Okay? So now you will go through all the description to finish the design of this device, including the circuit here and also the MEMS device here. Okay? This is for the next homework. Not easy. For this one, it easily take you 3 to 4 days to finish it. And plus the other one I just mentioned, you need to go through hundreds of times of the fabrication process, is this one. This will take you 2 or 3 days. So in total, it was easy spend you 1 or 2 weeks to finish the homework. Okay, so I will give you the homework this week. So hopefully in 2 weeks you can have good results. Okay. So I think that's it. Just a little bit of description of this homework.